Hello everyone. In this unit of constant velocity, which are caused by balanced forces, we have done a lot of ways of modeling those balanced forces, whether that's a system schema or our new thing, the force diagram. And in every one of those cases, there's always been one force that's been there, right? And that is the force of gravity, the force between an object and the Earth. Right? Well, we're going to do a little lab and learn a little bit about the force of gravity and take a little deeper dive into that force of gravity. So, here we have two football players. See what I did there? See what I did there? Right? Two football players. Right? Are the forces of gravity acting on them different or the same? Think about that. Well, before we actually start to draw the force diagrams or anything like that, let's change the verbiage a little bit here. You generally don't talk about the force of gravity acting on you. You know, when you step on the scale in your bathroom, you don't say, I wonder what the force of gravity is acting on me this morning. And instead, you use a different term. And that different term is how much you weigh. So weight is the force of gravity acting on an object. I know that's kind of weird that there's two terms for the same thing, but that's just how the way it works here, right? And we can use them interchangeably. So if we're being technical, drawing a force diagram, drawing a system schema, we often talk about the force of gravity. But in more common language, we often talk about an object's weight. So we could say, an object has a certain weight, or if we want to be physics technical, we could say the force of gravity acting on that object. So kind of go back and forth. So let's rephrase this question then. Do you think those two football players weigh the same? Well, from the picture, my guess would be no. Well, why not? Right? Why don't those two football players weigh different? Get it? Right? What's fundamentally different about them that my guess is make this one weigh more than this one? Well, the fundamental thing might be, say, their mass. And so we're going to do a little lab here to see if there is a relationship between how much something weighs, how much force of gravity acts, and its mass, right? Mass being a more fundamental thing, how much matter is in the object. And therefore, the purpose of this lab is to create graphical and mathematical representations of the relationship between the force of gravity and the mass of an object near the surface of the Earth. I'm only going to guarantee these results near the surface of the Earth, and we'll see about how that affects things when we get to the post-lab. Well, this lab's kind of interesting because we're going to do this lab two different ways. Okay, we're going to watch a movie to do this lab, basically because of the COVID, right? So one way that we're going to use this lab is we are going to hang masses from something called a spring scale. Okay, this is a spring scale. Actually, most scales you're familiar with that are mechanical, not electronic ones, all right, but mechanical scales, like most bathroom, cheaper bathroom scales or the scale you might see at the grocery store, and have a spring inside of them. Okay? Ours is a little cylindrical spring. Right? It's a nice linear spring that's inside of a plastic tube here. And we can hang masses from it. Right? Here's some masses along with a mass hanger, and we hang it, and it stretches the spring. And although you can't see it in this picture, you'll be able to see it in the movie, it shows how much it weighs right on the scale. Okay? So we're basically going to add different masses and read the different weights or forces of gravity. So how does this all work? Well, let's do a quick system schema and a force diagram so we understand how the spring scale is doing this here. Okay, so first off, if we're going to look at the masses, what are the masses here, right? What are they interacting with? Well, of course, the whole point of this lab, right, is to investigate the interaction between the masses and the Earth, which we have called the force of gravity, or weight. By the way, that's why some books, some physics teachers will use a capital W instead of F of G. I like F of G because that tells us what it is, force of gravity, but some will use a capital W for weight. Well, something's holding up these masses, right? They're not falling because of that force of gravity. Now, there's no surface underneath it, notice. There's no table under here, right? So what's holding it up? Well, the spring scale is holding it up. And so this force we are going to call the force exerted by the spring, or the spring scale. Technically, it's not a tension force. Okay, springs exert forces, but we call them spring forces to be technical because they follow little different patterns, okay, that we'll eventually investigate, but not so much in this unit. So this is the force exerted by the spring. Are the masses interacting with anything else? No, that's it. Okay. So if we focus on the masses, we see that we have two forces going on here. So let's draw a quick little force diagram. There's the masses. We have the force of gravity, which of course will act down. We've got the force exerted by the spring, which will act up. All right, you stretch it down, it pulls back up. How big will those forces have to be? Well, what kind of motion? No motion. Constant velocity motion, so they have to balance. Note the lack of an arrow, because I'm not saying they're exactly the same. They're in different directions, but their sizes are the same. So basically, if we measure the force that the spring is exerting, which is what we're actually measuring with the spring scale, in this case of how we're doing the lab, that's equal to how much the masses weigh, the force of gravity acting on them. So we're inferring their weight, all right, by using the spring scale. With me there? Okay. Well, you're actually going to see this lab done two different ways in a little movie you're going to watch to do this lab. And the other way, we're going to get super high tech. This is actually a frame out of the movie. You can see over here, here's our spring scale. There's masses hung from it. Okay, you can't see those because I had to focus in so that we could actually try to read the scale. You can see here 0, 1, 2, 3. We'll talk about what those mean in a little bit. All right, little hash marks here. If that's a 2 and that's a 3 are the dark ones, that's 0.2, 0.4, 0.6, 0.8. Every little hash mark's worth 0.2 on this scale. Right? And we can read up here this little thing and try to decide what that is. But over here, we're going high tech. This is a cart we're eventually going to use in lab. It's got a lot of fancy things to it. It's a Bluetooth cart. But one of the things it has in it is a force probe. Okay, a force probe. There's a little what's called a strain gauge inside, little piece of metal, and depending on how much strain is put on it, it converts that to a force. Okay, it's a little electronic device, if you will. It Bluetooths to the computer, and what it reads is right behind on the screen that you'll see in the movie. Okay, notice I've got masses hung there. Basically, I have the same amount of masses hung here as I do here. Right? You just can't see them on the spring scale because I had to focus in. Right? But you can see them over here. And you'll see in the movie that I announce how much mass I'm hanging, and then I hang it from each scale, right? You can read it, and then 20 seconds later, I hang a different amount of mass, and then you can read it on both scales, okay? So we're going kind of high tech and lower tech here at the same time. Kind of as we do more labs with forces in other units, we tend to go higher tech to do different things, but it's nice to do kind of a low tech version of this as well with springs because they're a little easier to wrap your brains around. Okay? So this is the two different ways you're going to see in the movie. So, we're going to control the amount of mass that we hang on the spring scale or the force probe. So that makes it the independent variable. The force of gravity will be what we'll measure. That will be our dependent variable. So when it comes time to graph, you're going to make graphs of force of gravity versus mass. Right? Mass on the independent is the independent, so the horizontal axis, force of gravity on the vertical axis. Now, we have not talked about a unit yet for force, right? We've drawn a lot of forces, different kinds of forces, but we've never really talked about what we're going to measure them in. Well, like many things, there is a special metric or SI unit for force, and it is named after Sir Isaac. It is called the Newton. Because it's named after a person, it is denoted by a capital N. Don't know if you know that or not, but most often units are capitalized if they're named after people. They're lowercase if they're not. Right? That's not always true, but it's a good rule of thumb. Right? For example, there is no Mr. Meter, which is why it's a lowercase m. Right? There is no Mr. Kilogram, so it's a lowercase kg. Right? But a Newton, named after Isaac, is a capital N. Now, you've probably never heard of this unit before. Even in Europe, they don't really use this unit. They use something else, okay? Well, what do we use here to measure forces? We'll think about weights. Right? You get on the bathroom scale, what is it measured in here? Pounds. So for now, I want to give you an idea of how much a Newton is in terms of a force. Right? So I'm just going to compare it to pounds. So 1 Newton is a little less than a quarter of a pound. It's 0.2248 pounds. Little less than a quarter of a pound. So it's a pretty small unit of force. 1 Newton of force. And this, by the way, our force probe will read in newtons. The spring scale even reads in newtons, so unlike a bathroom scale, say. Right? 1 pound is a little less than 4.5 newtons of force. You kind of reverse it. Right? But a good way to think about this here is that 1 Newton is a little less than a quarter of a pound, 0.2248 pounds if you got to convert, okay? But keep that in mind. So a Newton is a much smaller unit, right? So you might say, hey, you know, here's a guy that weighs 400 newtons. But before you think it's some huge guy, it's not, right? Because it's really, that would be less than 100 pounds, right? Because it's a little less than a quarter of a pound in 1 Newton, right? So you got to keep in mind that a Newton is a smaller unit than a pound. Right? So we're going to measure everything here in newtons. You're going to have a data table on your lab sheet. These are the different masses. It starts with 0.1, 0.2, all the way up to 1 kilogram of mass. And again, in the movie you're going to watch, I'm going to call that out as I add those masses to the scales. And then you're going to write down the force of gravities. You can see it high-tech on the one half of the screen, and you can use the spring scale on the other half of the screen and hopefully, you know, agree that both are reading the same. But to read the spring scale, you got to be a little careful. You've got to estimate, estimate, estimate. Don't just round off to the nearest hash mark. Try to estimate in between. But remember, on the spring scale we're using, the nearest hash, or every hash mark, sorry, is about 0.2 newtons. Right? They're big, dark 1, 2, 3, 4, 5, all the way up to 10 newtons. Okay, all the way up to 10. But each little line in between is 0.2. Okay, and that should help you read the spring scale. But remember, you've also got the high-tech scale to look at. So in this case, because we're going to go kind of touchless in this lab, right? You're going to watch this video. You can watch it as many times as you need to get all the data. Once you've got the data down, then it's into graphical analysis. You'll make a graph, and we'll go from there. Right? What does the slope mean? Math model, all of that good stuff. And then we'll do a post-lab where we'll talk about all the parts as we learn more deeply about the relationship between the force of gravity, how much something weighs, and the more fundamental quantity of mass.